In the last few videos, we've introduced the idea of energy conservation and the work kinetic energy theorem. I'm going to take a bit of a turn here for a moment and introduce restoring forces. We will eventually find the work that they do, but first I want to bring up the idea of a restoring force. I'll start by talking about it generically. There are many physical situations where an object will have some equilibrium position. So I'm just going to note that here with this dashed line. So if the object is just plain sitting there and it's in what we call a stable equilibrium, and we'll get to what that means later, it won't feel any force, any net force on it. It will just sit there. But if it is what we call a stable equilibrium, if it gets displaced off of equilibrium one way or the other, what will happen is there is some sort of force happening, and it could be due to almost anything. Now I'll give some examples in a moment, that will try to put it back to its original position. So for instance, if the object ended up over here, let's say, what would happen is that it would feel a force trying to push it back towards the equilibrium position. And similarly, if it were over here, it would feel a force trying to push it back towards the equilibrium position. Any sort of force acting on an object in this sort of a situation, we call a restoring force. And there are plenty of examples of this. And sometimes it's a collection of forces. So for instance, an atom sitting in, say, in a salt crystal. So we have some salt crystals here. The electrical bonds between the salt crystals are such that if the atom gets disturbed off of their equilibrium, off of its equilibrium position, the electric force between adjacent ions in a salt crystal will look to put the atom back into its original location. Now, like here, in this one I've drawn here, if this is a true salt crystal, there will be some atoms in the front and back as well. There'd be a grand total of 6 bonds, which are all just the electric force acting between adjacent atoms in the salt crystal. And if I say disturb it over this way a little bit, what will happen is the combined electric forces of all of the adjacent atoms will seek to return it back to its equilibrium position. So that's an example of a restoring force. Other examples of restoring forces can actually be gravity, for instance. Say if you have a planet that is orbiting the sun, if the planet were to get some sort of going around in orbit, if say the planet were to get hit with a very large impact or something like that, what will happen is its orbit will probably end up doing something like this. And it'll turn out that a piece of gravity will be acting as a restoring force, trying to keep returning the planet back to its equilibrium position, or the orbit it would have done before it got hit with the impactor. And so that would be an example of a restoring force there as well. That piece of gravity that's different from what you would expect for the normal situation. And the examples go on and on and on. The classic example that is used in introductory physics, especially since it has so much practical use for engineering, is a spring. So here I have a mass and I have a spring, and this would be the equilibrium position of my spring, of my mass on the spring. And the idea is, again, simply I go and put it over here. What will happen is the spring will stretch. And since the spring is stretched, it wants to return back to its original shape. And so in so doing, you would feel a spring force pulling it back towards the equilibrium position. And the same thing over here. Over here, so this would correspond to stretching the spring. And here, where we would compress it, the spring would try to be returned back to its original shape and would be pushing the mass, again, back towards the equilibrium position. So I haven't said so far what sort of, quantitatively, what these force laws look like. And in general, we can't say too much, other than that however the math of it works out, it's got to work out in a way that it pushes it back towards the equilibrium position. However, it can be shown, although in a more advanced treatment than this, if the displacement is small enough. You can model the restoring force with Hooke's law. As a side note here, Hooke was actually a contemporary of Newton, and he was working on universal gravitation at the same time that Isaac Newton was. It turns out that there are different possible force laws that could have given rise to stable orbits of planets around the sun. Newton correctly guessed that went inversely as the square of the distance. Hooke was playing with a different model, and although it turns out not to be correct for gravity, it does turn out to be very good for a spring. So what we will say is that so let me just carefully draw a spring here. So I've got myself a little wall, attaching my spring to it. So here is my equilibrium position. And let's just displace it off to the right. So to be perfectly general, although this is not the way people usually do this, we'll just imagine that we've got a ruler laying up against this. We'll just call this direction S, and it doesn't matter whether it's increasing in the direction of stretch or compression even, or where the zero is. I'll just put it here as an example. That would make this position here S equilibrium. And that would make this position where we're stretched S. And the amount of the stretch will be delta S. With that all defined in place, what we can say is that the force of the spring, or I should say the S component of the force of the spring, will be equal to minus K delta S, where K is just a proportionality constant. It's called the spring constant. And it's specific to the spring in question, although, again, this is more general than just springs. So in molecular data tables, bonds are often given effective spring different bonds are given effective spring constants, for instance, to describe, again, this restoring force property. So delta S is the amount of the stretch. So that would typically be in meters, and our spring constant then would be newtons per meter. so that we would get the force of the spring. And this is, the value of this is going, for a practical spring, it's going to depend on the details of the materials chosen to make it and how it's all coiled up and all that, all the manufacturing considerations. Now, what the heck is up with this minus sign? This minus sign here is what is the hallmark of a restoring force. So I'll say that that's just screaming out that this is a restoring force. And the reason here is, let's say here in this example where I have S increasing to the right, if I have displaced my object over to the right, we know that the spring has to exert a force to the left. So here, delta S would be positive in this example here. But we need the force of the spring to be negative. So thus the minus sign. And it works the other way. If, for instance, we were to have had a compression of the spring instead of a stretch, my delta S here, my delta S here would be negative, but I would need my force of my spring to be pointing to the right. So, okay. I would need the force of my spring to be pointing to the right, or I should say against the direction of compression. So that would force me to have the spring force component, be positive. So again, this is an algebraic minus sign that encodes that the force points opposite the stretch. The stretch or compression. Okay. And it's been proven that any restoring force for a small enough displacement will always can always be modeled like this. Now, if it gets bigger, what you'll have to do a more complicated model, and the details of that model depend on the forces involved, whatever. It can look pretty complicated, but as long as the displacements are small, this works out. And it turns out a lot of times, yes, they are small enough displacements that we can go ahead and use this successfully. If not, there are tricks that you can sometimes use to correct for slight deviations off of this linearity. But again, that's beyond the scope of this treatment. Now, if you've had some brush with physics before, you probably didn't see Hooke's law written like this. This is the most general way that you can possibly do it. But what's often done is you create what's called a generalized coordinate. That's just a fancy bit of jargon. It basically says that I'm going to create a coordinate system special to the spring. And usually the name you give it is X, and in the stretch direction, X will be positive. In the compression direction, X will be negative. And, it will be negative. And at the equilibrium position, you say that X is 0. So if you make that specific choice of special coordinate system just for the spring itself, you can instead write this as minus kx. So the official super general version is this bit right here, but 99 and 44/100% of the time you can get away with creating a special coordinate system for the spring. But you know, on the off chance that you say you got a measuring rig or something like that, where for whatever reason 0 isn't where you need it to be, then it isn't at the equilibrium position, then this version is always there for you. All right, so with that, let's go ahead and calculate the work that a spring can do, and then we can use the work kinetic energy theorem to do an example problem. So let's try, and again, this is actually work done by any restoring force, but we're just going to say work by a spring because this is the example we're thinking about. And I'm going to go ahead and do the thing of saying let x equals 0 be the equilibrium position. At the end, I'll translate back into the more generic delta S expression, but I think that it'll be a little easier to think about this way. So let's make a plot of, actually let's do a better job of it than that. Let's make a plot of the force that our spring exerts as a function of our stretch. And this x here, remember, is our stretch or compression that we're measuring. The general curve of the general curve for this is going to look like, whoops, there we go, like this. Because the force of the spring is minus kx. So the slope of this curve here is minus k, again, where k is the spring constant. And remember, again, what the sign is telling us here is that over in this area you have a compression, and the force, the spring is trying to stretch, try to expand back out to its original length, and it will try to push the mass out of its way. And here you have a stretch, and the spring is again trying to retract back to its original length, and it's going to try to drag the object along with it. Okay, so if I want to, so let's say that we'll just pick this point here, and this point here. The general result will be true no matter what. So let's say that my object is initially here, and I grab it with my hand or something and pull it to this position x final. How much work did the spring do? Well, if we go back, we remember that the definition of work is the integral of the force with respect to the displacement from x initial to x final. So this will be from x initial to x final dx. Here I'll be integrating minus kx. Now again, this is a thing that you can just up and look up in integral tables. And so I'll go ahead and give the answer right now, is that it will be equal to minus 1/2 k x final squared minus x initial squared. But let's go ahead and prove that, shall we? So the idea here is that this integral here is always equal to the area under the curve, that bounded by the x-axis, our force function, and x initial and x final. So this area right here is the work. So first off, we notice that the work is under the curve as we've drawn it here. That's going to give us a minus sign for the area. Okay, that works out. Now for the next bit of it, we can note that this y-coordinate here is minus kx final, and this y-coordinate here is, oh, sorry, I shouldn't say y, I should say force. So here, the force of the spring is minus kx final, and here the force of the spring is minus kx initial. Now the way I can find the area of this is the area of a trapezoid. So we can go ahead and say that this area here, so we have the minus sign again because it's underneath here. The area of trapezoid will be this distance here times this average height right here. So this distance here is x final minus x initial. The average height will be 1/2 x final plus, sorry, 1/2. Let's call this f spring final and f spring initial, just to be careful. 1/2, oops. There we go. 1/2 f spring final plus f spring initial. Now I've already taken care of the minus sign here, so we're just working in magnitude right here, so I'm going to drop these minus signs. So this is minus x final, sorry, minus 1/2 x final minus x initial. Now this bit here is going to give me a kx final, and this will be plus kx initial from Hooke's law. And again, I've already taken the minus sign, I've already taken the minus sign into account by noticing that the area is negative. All right, well, I can pull out a k here, so this will be minus 1/2 k. Now I've got x final minus x initial times x final plus x initial. We remember from algebra that's x final squared minus x initial squared. So that is indeed our work done by the spring. Now I did this in the super special coordinate system where x equals 0 at the equilibrium position. The general expression, if for some reason it's not practical to make that choice of coordinate system, is to say it's 1/2 k times delta s final squared minus delta s initial squared. And that's again the same thing. It's just this is the final stretch, the initial stretch. I'll leave it as an exercise for the viewer to convince themselves that no matter where they put x final and x initial anywhere along here, you'll always get this same result. So let's just go ahead and do a quick example of this using the work kinetic energy theorem. So let's just say you've made yourself a little toy spring launcher here. Let's say it's 10, it has a spring constant 10 newtons per meter, and you got yourself like a little metal sphere, let's say mass of 10 grams, so 0.01 kilograms. So we'll say this is the equilibrium position of it. And what we're going to do is we're initially going to compress the spring like so. And there's a plunger right here, which we'll assume is massless, attached to our massive sphere. This is going to go ahead and expand out to the equilibrium position, and then once the plunger gets over here somewhere, this is just going to go flying off. So what I'm interested in finding out is, okay, what is the final speed of our mass here? Well, we can use the work kinetic energy theorem to get that. So the net work will be equal to the change in the kinetic energy. So that'll be K final minus K initial. This is 1/2 mv final squared minus 1/2 mv initial squared. And initially, we're starting at rest, so we can make that term go away. Now, the work being done here is going to be, oh, I forgot how much I was going to compress this by. So let's go ahead and say x equals 0 here. So I'll use the special version where x equals 0 at equilibrium. So this will be my x final, my x initial here. Let's just say we compress it to 10 centimeters. So my x initial will be negative 0.1 meters, like so. All right, so the net work we just saw will be minus 1/2 k x final squared minus x initial squared. Now x final is 0, and here I have a minus. So the work done will be positive 1/2 k x initial squared, and that'll equal 1/2 mv final squared. Hey, we can cancel the halves for what that's worth. We get that v final will be equal to the square root of k over m times x initial. All right, so that's going to be the square root of 10 newtons per meter over 0.01 kilograms times minus 0.1 meters, but we'll be squaring. Whoops, sorry. Yeah, minus, x squared there, minus 0.1 meters squared. Now, a quick note here. You'll notice that while I was doing this, I made a mistake. And it's worth just a quick moment to see how I caught my mistake. The way I caught my mistake here was, as I was going along, I dropped the squared. And when I started to substitute this in, I realized that I was going to have a positive square root. That's good. We're expecting that. But when I was going to stick in my x initial, I was going to have a negative number there. And I know that a final speed being negative wouldn't make a lick of sense. So that's how I knew that I messed up my math, somewhere. And that's where I went ahead and started checking where I could have messed that up at. So, and then I realized I dropped the squared. So anyway, if you grind this through, you'll see that our final speed is 0.32 meters per second, meters per second, which seems like a perfectly plausible number, 32 centimeters per second. If you got a fairly lightweight ball bearing and the end of a stiff spring, that seems to make some sense. All right, in the next video, we will introduce thermal energy for a bit and then talk about power. Catch you over there.